Chapter 9, Counting and Probability, Possibility Trees, and the Multiplication Rule. A tree structure is a useful tool for keeping systematic track of all possibilities and situations in which events happen in order. The following example shows how to use such a structure to count the number of different outcomes of a tournament. Teams A and B are to play each other repeatedly until one wins 2 games in a row, or a total of 3 games. One way in which this tournament can be played is for A to win the first game, B to win the second, and A to win the third and fourth games. How many ways can the tournament be played? And assuming that all the ways of playing the tournament are equally likely, what is the probability that 5 games are needed to determine the tournament winner? The possible ways for the tournament to be played are represented by the distinct paths from a root, or the start of the tree. Going from the root to a leaf, which is a terminal point of the tree. The tree diagram here, shown sideways, shows all the possible branches of the tournament and possibilities of the tournament. A terminating leaf indicates a end to the tournament, and these are the different possibilities and for how the tournament can play out. The fact that there are 10 paths from the root of the tree to its leaves shows that there are 10 possible ways for the tournament to be played. In 5 cases, A wins, and the other 5 cases, B wins. The least number of games that must be played to determine a winner is 2, and the most that will need to be played is 5. Since all the possible ways of playing the tournament are listed in Part A are assumed to be equally likely, the listing shows that 5 games are needed in 4 different cases. The probability that 5 games are needed is then 4 out of 10, or 40%. The multiplication rule. Consider the following example. Suppose a computer installation has 4 I/O units and 3 CPUs. Any I/O unit can be paired with any CPU. How many ways are there to pair an input-output unit to a central processing unit? To answer this question, imagine the pairing of the 2 types of units as a 2-step operation. First, you choose the I/O unit. Then step 2, you choose the CPU. The possible outcomes then can be illustrated in the possibility tree here, where the first step is represented by the first layer, followed by the second step. The topmost path from the root to leaf indicates that input-output unit A is to be paired with CPU X. Next lower branch indicates I/O unit A is to be paired with CPU Y, and so forth. Thus, the total number of ways to pair the 2 types of units is the same as the number of branches of the tree, or rather leaves of the tree, which is 4 times 3. There are 4 groups of 3. Also, there are 4 branches here, times the 3 leaves on each branch is equal to 12. The idea behind this example can be used to prove the following rule. If an operation consists of k steps, the first step can be performed in n1 ways. Second step can be performed in n2 ways, regardless of how the first step was performed. And the kth step can be performed in nk ways, regardless of how the preceding steps were performed. Then the entire operation can be performed in n1 times n2 times n3, etc., times nk different ways. So let's use the example of a personal identification number that is required to be a sequence of 4 symbols chosen from the 26 uppercase letters in the Roman alphabet and the 10 digits. How many different pins are possible if repetition of symbols is allowed? How many different pins are possible if repetition of symbols is not allowed? What is the possibility that a pin does not have a repeated symbol, assuming that all pins are equally likely? You can think of it as a 4-step process. You have if you allow repeating, you have 36 options for step 1, 36 options for step 2, step 3, and step 4. So the total number of options would be 36 times 36 times 36 times 36, or 36 to the 4th power, leading to a little over 1.6 million pins possible. For forming a pin without repetition, first choose you choose the first symbol, then the second, third, and fourth, but there are 36 ways to choose the first symbol, 35 ways to choose the second, since the first symbol cannot be used again, 34 ways to choose the third, since the first 2 symbols cannot be reused, and 33 ways to choose the fourth, again, because the first 3 symbols cannot be reused. Thus, the multiplication rule can be applied to conclude that there are 36 times 35 times 34 times 33, or 1.4, a little over 1.4 million different pins without a repeated symbol. Now, what's the likelihood of a pin not having a repeated symbol? Part B, there's 1.4, a little over 1.4 million pins with no repeated symbol. And from part A, there's a little over 1.6 million pins in all. Thus, the probability that a pin chosen at random contains no repeated symbol is 1.4 million over 1.6 million, or 0.8417, or approximately 84% of pins have no repeated symbol. Consider the following loop. Nested loop. Like you're going over a 2-dimensional array. The outer loop has repeats 4 times, the inner loop 3 times. How many times does the inner loop go through when the algorithm is implemented and run? Well, the outer loop is iterated 4 times, and during each iteration of the outer loop, there are 3 iterations of the inner loop. So by the multiplication rule, the total number of iterations of the inner loop is 4 times 3. Now, permutations. A permutation of a set of objects is an ordering of the objects in a row. For example, the set of elements A, B, and C has 6 permutations. In general, given a set of n objects, how many permutations does the set have? Well, you can imagine it forming a n-step operation where you choose the first element, then you choose the second element, then the third element, etc., to the nth element. Any element of a set can be chosen in step 1, so there's n ways to perform step 1. Any element except the one chosen in step 1 could be chosen in step 2, so there are n minus 1 ways to perform step 2, and so forth. In general, the number of ways to perform each successive step is 1 less than the number of ways to perform the preceding step. At the point where the nth element is chosen, there's only one element left, so there's only one way to perform it. So, by the multiplication rule, do it all out, and it comes to n factorial ways to perform the operation. In other words, there are n factorial permutations of a set of n elements. This reasoning is summarized in the following theorem. For any integer n with n greater than or equal to 1, the number of permutations of a set with n elements is n factorial. How many ways can the letters in the word computer be arranged in a row? How many ways can the letters in the word computer be arranged if the letters C and O must remain next to each other as a unit? If letters of the word computer are randomly arranged in a row, what is the probability that the letters C-O remain next to each other as a unit? Well, first, all 8 letters in the word computer are distinct, so the number of ways in which they can be arranged equals the number of permutations of a set of 8 elements. Therefore, it would be 8 factorial, or a little over 40,000. If the letter group CO is treated as a unit, then there are effectively only 7 objects that are to be arranged in a row. Hence, there are as many ways to write the letters as there are permutations of a set of 7 elements, namely 7 factorial. And finally, when the letters are arranged randomly in a row, the total number of arrangements is 40,000-ish by part A, and the number of arrangements with the letters CO next to each other is 5,000-ish. Thus, the probability that a random ordering will have the CO together would be 5,000 over 40,000, or 12.5%. Permutation of selected elements. Given a set of the elements A, B, and C, there are 6 ways to select 2 letters from the set and write them in order. Each such ordering of 2 elements is called a 2 permutation. An R permutation of a set of n elements is an ordered selection of R elements taken from the set of n elements. The number of R permutations of a set of n permutations, of n elements, is denoted P of n and R. If n and R are integers and R is between 1 and n, then the number of R permutations of a set of n elements is given by the formula n times n minus 1 times n minus 2, etc., times n minus R plus 1. Or equivalently, if you want a slightly easier notation, P of n and R equals n factorial over n minus R factorial. So evaluate P of 5 and 2. How many 4 permutations are there of a set of 7 objects? How many 5 permutations are there of a set of 5 objects? Well, you can multiply out, expand out the 5 factorial this way and cancel out the 3 factorial and leaves you with 5 times 4 is 20 for 5 and 2. The number of 4 permutations of a set of 7 objects, again, you expand it out Cancel out the 3, leaves you with 7 times 6 times 4 times 5 is 840. Now the number of 5 permutations of a set of 5 objects is going to be the same as how many permutations are there of a set of 5, because 5 minus 5 factorial is 0 factorial, or 1. Therefore, it's 5 factorial over 1, which is equal to 120. Always happens this time. All right. All right, that's it for this section. And then we'll get into the addition rule. In the next section here. Counting elements of disjoint sets. Now, 2 sets are disjoint if they do not share any common elements. This is something that will be covered in chapter 6 if you choose to do the extra credit. But just for terminology purposes, a disjoint set, 2 disjoint sets have no common elements, or the intersection of the 2 sets is the empty set. So, counting element of a disjoint set. This can be solved by counting the numbers of elements in the union of 2 sets, the difference of 2 sets, or the intersection of 2 sets. The basic rule underlying the calculation of the number of elements in a union or difference or intersection is the addition rule. This rule states that the number of elements in a union of mutually disjoint finite sets equals the number of elements in each of the component sets. So n of a, if it's a finite set, is the sum of the number of elements of each added to each of the subsets, disjoint subsets. The sum of those numbers of elements added together. So how many 3-digit integers from 100 to 99 are divisible by 5? We had this problem, we used this example in a previous lecture. This is another approach. The solution to this problem uses this method uses the addition rule. Integers that are divisible by 5 end in either 5 or 0. Thus, the set of all 3-digit integers that are divisible by 5 can be split into 2 disjoint subsets, A1 and A2 shown in that figure 931. This set is separate from this set, but and disjoint. They don't have any common elements because they end in different digits. Now, there are as many 3-digit integers that end in 0 as there are possible choices for the leftmost and middle digits. How many possible choices there are for those? So there are 9 choices for the leftmost digit, because you can't have 0 in the first digit. And there are 10 choices for the second digit, and just 1 choice for the third digit. It has to be end in 0. So it would be 9 times 10, or 90. Similar reasoning shows that there are as many 3-digit integers that end in 5s as there are possible choices for the leftmost and right and middle digits, which ends up being 90 as well. So the sum of the number of the number of 3-digit integers that are divisible by 5 is equal to the number in the set of integers that end in 0 and the set of integers that end in 5 added together. 90 plus 90 is 180. And if you recall from the previous lecture, we came to the same conclusion by a different route. The difference rule. An important consequence of the addition rule is the fact that if the number of elements in set A and the number in a subset B of A are both known, then the number of elements that are in A but not in B can be computed. If A is a finite set and B is a subset of A, then the number of elements that are in A but not in B is equal to the number of elements in A minus the number of elements in the subset B. The difference rule is illustrated here in this figure. The difference rule holds for the following reason. If B is a subset of A, then the two sets B and A minus B have no common elements, and the B union with A minus B is equal to A. That symbol there is the union symbol, which you will learn more about in Chapter 6 if you do the extra credit. I'm going to do a little thing at the end about these symbols that you're going to see through the course of this lecture. So by the addition rule, n of B, the number of elements in B, plus the number of elements in A minus B is equal to n number of elements in A. Subtracting the number of elements of B from both sides gives us the equation. The number of elements in A minus B equals n number of elements in A minus the number of elements in B. Consider the personal identification numbers problem again. There are a little over 1.6 million pins with repetition allowed, and a little over 265,000 pins with no repeated symbol, as was calculated earlier. How many pins contain at least one repeated symbol? If all pins are equally likely, what is the probability of randomly choosing a pin that contains at least one repeated symbol? So you would have S be the set of all pins, and A be the set of pins with no repeated symbol. As we calculated earlier in the section, 1.6-ish million total pins, and 1.4-ish million pins with no repeated symbol. By the difference rule, then the number of pins that contain at least one repeated symbol is about 265,000. Now, the probability that you're going to come up with a pin that has a repeated symbol can be done 2 different ways. You can use the equally likely probability formula and plug in the numbers and get 0.158 or 15.8% likelihood of getting a pin with a repeated symbol. The other method is to use the probability of A has being a probability that a randomly chosen pin has no repeated symbol. So P of S minus A is the probability that a randomly chosen pin has at least one repeated symbol. Now P of S minus A is equal to N of S minus A over N of S, which equals N of S minus N of A over N of S. Separate those out by the law of fractions. M equals N of S over N of S minus N of A over N of S, which equals to 1 minus P of A. So, which would in this case equal to be 1 minus 0.842 or 0.158 and 15.8%. Formula for the probability of the complement of an event. If S is a finite sample space and A is an event in S, then the probability of the complement of A occurring is 1 minus the probability of A occurring, where the complement of A is equal to S minus A. All right. A certain computer access password consists of 3 through 5 uppercase letters chosen from the 26 letters in the Roman alphabet, with repetitions allowed. Not a very secure password, but to each their own. How many different passwords are possible? How many different passwords have no repeated letter? How many different passwords have at least one repeated letter? If all passwords are equally likely, what is the probability that a randomly chosen password has at least one repeated letter? Now, start with how many are possible. You have 3 sets, the set of passwords of length 3, the passwords of length 4, and passwords of length 5. I should say they are subsets of the whole set, the set of all passwords allowable. By the addition rule, the sum of the passwords equals the number with length 3 plus the number with length 4 plus the number with length 5. Multiplication rule can be used to compute the number of passwords of each length. 26 to the 3rd power for passwords with length 3. 26 to the 4th power for passwords with length 4. And 26 to the 5th power for passwords with length 5. Hence, the number of total number of passwords is 26 to the 3rd plus 26 to the 4th plus 26 to the 5th equals a little over 12.3 million passwords. Now, constructing a password with length 3 with no repeated letter is a 3-step process with 26 steps for choices for step 1, 25 choices for step 2, and 24 choices for step 3. So there is 26 times 25 times 24 passwords with a length 3 with no repeated letter. Similar logic can be used to determine how many passwords with no repeated letter of length 4 and 5 by doing those multiplications out. So the total number of passwords with no repeated letter is all this multiplication and addition and all that sort of stuff leads you to 8.2 million passwords. Now, by C, or by part A, the total number of passwords is 12.3 million, and by part B is 8.2 million that do not have a repeated letter. Thus, by the difference rule, the number of passwords with at least one repeated letter is about 4 million passwords. Finally, given the assumption that all passwords are equally likely, the probability that a random chosen password has at least one repeated letter is the number of passwords with no repeated letter over the number of passwords with no repeated letter divided by the total number of passwords, which is 33.1%. I think there's a I'll screw up in the text there. The inclusion-exclusion rule. The addition rule says that how many elements are in a union of sets if the sets are mutually disjoint. Now consider the question of how to determine the number of elements in a union of sets when some of the sets overlap. For simplicity, begin by looking at a union of two sets, A and B, where the intersection of A and B is the darker shaded area in the middle where the two sets overlap. All right. Now, if you add them together, if you add the number of elements in A and B together, you'll get too many elements because there are some elements that are in both. So what you have to do is, for the union of A and B, add the number of elements in A plus the number of elements in B, then subtract the number of elements in both A and B. Because those get counted twice, you have to take that number away one time to get the actual total number of elements. So, how many integers from 1 to 1,000 are multiples of 3 or the multiple of 5? The little intersection union of sets here. Let A be the set of all integers from 1 through 1,000 that are multiples of 3. Let B equal the set of all integers from 1 through 1,000 that are multiples of 5. Then A union B is the set of all integers from 1 through 1,000 that are multiples of 3 or multiples of 5. And A intersection B be the set of all integers from 1 through 1,000 that are multiples of both 3 and 5. So, which then would equal to the set of all integers from 1 through 1,000 that are multiples of 15. Because every third integer from 3 through 999 is a multiple of 3, each can be represented in the form of 3k for some integer from k, some integer k from 1 through 333. Therefore, there are 33 multiples of 3 from 1 through 1,000. Similarly, each multiple of 5 from 1 through 1,000 has the form of 5k for some integer k from 1 through 200. Thus, there are 200 multiples of 5 from 1 through 1,000. Finally, each multiple of 15 from 1 to 1,000 has the form of 15k for some integer k from 1 through 666. I mean, from 66 through 66. Since 990 equals 66 times 15. Therefore, there are 66 multiples of 15 from 1 through 1,000. And the number of the intersection of A and B equals 66. It follows by the inclusion-exclusion rule that n of A union B is equal to n of A plus n of B plus n of A intersection B. I'm sorry, that should be a minus symbol. That's a typo in the slide there. Which is equal to 333 minus or plus 200 minus 66, which is 467. Therefore, there are 467 integers from 1 through 1,000 that are multiples of 3 or multiples of 5. And we didn't go over that one, so I think that's it. Yeah. Now, a little set notation that you get in chapter 6. Elements in A or B combined and A intersection B is equal to the elements in A and B. Now, this is called the intersection. Now, the easy way to remember this is the U shape for union, and the other one is the intersection. So, going back to the beginning of the semester with the and ors, the or symbol was the V-ish symbol, and the opposite was the and symbol. So, intersection is the elements that are in A and B. So it's open down like the and symbol from the beginning of the semester. Likewise, this is open up like the or symbol. So this is all the elements that are in A or B combined into one set. So that's the easy 5-cent tour of union and intersection.